everyone. In this video, let us study about variance properties and characteristic functions. Expectation can be seen as a linear operator. Linear expectation operator can be seen with the transformation y is equal to ax plus b. It's a straight line equation. B is the intercept, a is the slope. The mean of the random variable y, we have already defined in the previous video, mu y is equal to expectation of y. We replace y with ax plus b, so we get expectation of ax plus b. Since it is linear in nature, we will separate this out. So expectation of ax plus expectation of b. Since b is a constant, expectation of b is also a constant b. So here a is a constant, it is taken out. So it is a into expectation of x. Expectation of x, we have called it as mean, that is mu x. So this is equal to a into mu x plus b. Similarly, the variance y can be represented as sigma y whole square is equal to expectation of y minus mu y whole square. So that is expectation of y is given as ax plus b, and mu y we have already derived it as a mu x plus b. Substituting this here, we get minus a mu x minus b. So b and b will get cancelled out. So we have ax minus a mu x. So therefore it is a square x minus mu x whole square. So expectation of a square into x minus mu x whole square. So a square is a constant term that is taken out. It is the expectation of x minus mu x whole square. And this is defined as sigma x whole square. That's the variance of x. Let us study the properties of variance. First one, let g be a function and a and b are constants. For any random variable f, be it discrete or continuous, variance of a into g of x plus b is given as a square into variance of g of x. In general, we have already derived it in the earlier slide. Variance of ax plus b is equal to a square variance of x. Second one, if x and y are independent random variables, then variance of x plus y is always given as variance of x plus variance of y. It is not the case if there is a dependency between x and y. If they are not independent, then variance of x plus y is equal to variance of x plus variance of y plus 2 times covariance of x comma y, where covariance of x comma y is defined as expectation of x minus mu x into y minus mu y. That is the expectation of x y minus mu x into mu y. Covariance is a measure of the relationship between the two random variables. We'll take an example. We need to transform the random variable x to any other random variable y uniformly distributed between y1 and y2. So y is defined as y2 minus y1 into x plus y1. Here you can observe that it is in the form of ax plus b, where a is equal to y2 minus y1, b is equal to y1. The mean of y, mu y, is equal to a into mu x plus b. So it is B is given as y1 and A is given as y2 minus y1 and mu x for uniformly distributed function is half. Therefore, we have A into mu x is equal to y2 minus y1 by 2 plus y1, that is equal to y2 plus y1 by 2. The variance of y is defined as sigma y square is equal to y2 minus y1 whole square by 12, which we have already derived in the previous video. Let us define the characteristic functions of random variables. Let x be a random variable, then the characteristic function of x is defined as phi x of j omega is equal to expectation of e to the power j omega x. That is, the integral of fx of x e to the power j omega x dx, where we know that e to the power j omega is defined as cos omega plus j sin omega. The characteristic function phi x is similar to moment generating function mx. The characteristic function and the PDF are Fourier transform space. Therefore, we can obtain phi x of x, the PDF, as 1 divided by 2 pi integration of characteristic function e to the power minus j omega x d omega. Let us study the properties of characteristic function. First property says that phi of 0 is equal to 1. So we know that it is phi of x is given by e to the power j omega x, expectation of e to the power j omega x. In this case, x equal to 0, so expectation of 1, that is equal to 1. Similarly, we have another property, phi of minus x is equal to phi x of bar. This also can be derived in the same method. Third one, the modulus of phi of x, the absolute value of phi of x is always equal to 1. So here we know that when I take the absolute value here, absolute value of phi of x is the absolute value of e to the power j omega x. And we know that the magnitude of this is always equal to 1. So therefore, this is 1. And absolute value of phi of x plus x minus phi of x is always less than or equal to expectation of absolute value of e to the power jx minus 1. So phi of t is uniformly continuous on minus infinity to infinity. All these characteristic functions for different functions will be deriving it later. Fifth one, expectation of e to the power jx ay plus b is always equal to e to the power jxb, the characteristic function of x. Let us take one example where we need to find the characteristic function of a random variable x uniformly distributed between 0 and 1. So its value is going to be 0 to 1, its value is going to be 1. So therefore, integration of 0 to 1 e to the power j omega x dx will give us e to the power j omega minus 1 divided by j omega. Let us try to solve some problems. First problem, it is given that e of x equal to 2, mean x is equal to 2, and Ex square is equal to 6, that is mean of x square is equal to 6. We need to find the standard deviation of x. If y is equal to 6x square plus 2x minus 13, we need to find mu y, that is the mean of y. Given x bar, that is equal to mu x equal to 2, x square bar is given as 6. We need to find the variance of x, that is equal to standard deviation whole square is E of x minus mu x whole square. That is integral of x minus mu x whole square c df dx. And here you know that mu x is equal to 2. Let us substitute, we get this as x minus 2 whole square f of x dx. Now let us try to expand this x minus 2 whole square. When you expand this x minus 2 whole square, you get this as x square minus 4x plus 4. We'll use the principle of linear operation. So when we use this, we get this as first term is x square. So integral of x square pdf dx minus 4x fx of x dx under the integral sign plus integral of 4 fx of x dx. So this gives you ex square, this gives you 4 into e of x, this gives you e of 4. This is 6, this is minus 4 into 2 plus 4, answer is 2. Once we get the variance of x, standard deviation is always a positive quantity. So therefore, plus of root of variance of x. That is root of 2, that gives you 1.4142. Next, let us try to find out mu y. E of y is equal to E of x square plus 2x minus 13, and that gives you mu y. That is 6 into ex square plus 2 into e of x minus e of 13. So 6 into, here ex square is 6, 6 into 6 plus 2 into 2 minus 13. Answer is 27. Second problem, the random variable x has the expectation mu x is equal to minus 24, that is mu x, and sigma x, that is standard deviation, is equal to 3. The random variable y is obtained from x using y is equal to minus 2.7x plus 16. We need to find the mean of x square, ex square. We need to find the mean and the variance of y. So given x bar is equal to mu x, that is equal to minus 24. So sigma x is given to us. So sigma x square, that is variance of x, is defined as integral of x minus mu x whole square fx of x dx, that is x plus 24 whole square, the pdf dx. When we expand this, we get x square plus 48x plus 24 whole square fx of x dx, that is equal to 9. So 9 is equal to, the first term is x square, so ex square, plus second term is 48 e of x plus 24 whole square, that is e of 576, that gives you 576. Solving this, we can get ex square, that is equal to 585. Next, we need to find the mean and the variance of y. So E of y is equal to minus 2.7 E of x plus E of 16. That gives you minus 2.7 E of x plus 16. That is equal to mu y. E of x is given as minus 24. So minus 24 into minus 2.7 plus 16, that gives you 80.8. Variance of y is given as E of y square, that is equal to E of minus 2.7x plus 16 whole square, that gives you 2.7 whole square sigma x whole square. So that is 65.61. because sigma x is 3. So 2.7 whole square into 3 square, that is equal to 67.61. Thank you. In the next video, let us study some special distributions.